Hey everybody, I'm Chris, by the way. I guess we've got like another minute to start, but if you could get the resources from this link. I've put together some PD files in the Unity project and stuff that we're going to work with today. Yeah, it's a Google Drive link, yeah. Do you need a Google Drive account to access it?
No, it says you need permission.
Really? Oh, wait. Oh, shit, sorry about that.
Yes, a little bit.
I've got another solution. So the first hour, or first 45 minutes is going to be slides. So in the meantime, just pass it around and copy the Soundstack folder. No worries. Yeah, this isn't going to work because you need I haven't given the permissions for it. So just take the USB stick as it goes around. By the time we're working on it, you'll all have it. Okay, we're good to go? All right. So hey, everyone. My name is Chris. I used to go to university here. I did my PhD here recently in this exact domain of procedural audio or computational audio. Until August, I used to be one of the three members of Enzian Audio when we provided the Heavy compiler collection as a cloud service up until August. So I'm going to talk a bit more about what Heavy is and what it does, more and more towards the end of this workshop. But before we start, who's got Unity over here? Has everybody got Unity? OK, good. And Pure Data? You all got Pure Data?
The vanilla one.
Yeah. Yeah, vanilla. Hey, that's great. OK. So I realized not everybody here is like massively into the command line and using Python and the whole build tool system. So I've made it optional to use the Heavy compiler collection. I've provided lots of plugins and existing patches that we can dig into. But we'll go through this at the end, how to get it set up and get you up and running. But you don't need to worry about that for now. Because since we moved from the cloud to open sourcing this, it's all done locally on your own machine. So it means you need to have all your all the build chain ready. So you need to have Python, Xcode, or Visual Studio, and so on. OK. So this workshop is basically a workshop on computational audio, or rather, as it's also known as procedural audio. So I'm going to talk a little bit I'll try to make it not more than half an hour or so, about what computational audio is, why we need it, or why we want to use it, what its benefits are, and what tools are available to use it. And then after that, we're going to go through some Unity examples I've prepared. We'll also look at using the Resonance Audio SDK to spatialize our audio sources in Unity binaurally. And finally, we'll look at some PD examples, and as time allows, we'll go through the Heavy compiler and any other stuff that you want to do. So there'll be plenty of time at the end to play around, hopefully. Cool. I take it you guys have been doing some PD and kind of audio, like synthesis kind of stuff and spatialization throughout these few days. So hopefully this won't be too new to you. All right, so let's start. Um, computational audio or procedural audio, it comes from a person named Andy Farnell, who wrote a book called Designing Sound. He coined this idea of procedural audio. And the need for procedural audio, or this concept of procedural audio, arose from games, from game audio. Because in games, since about the early 90s, games have been heavily reliant on samples, so recorded sound. So the idea is press a button and you hear a sound. Similarly to the interaction with games, press a button and you jump or you walk and so on. So this is really good for the sound designer because you can add anything you want on top of an interaction like a button. However, when it comes to interactivity, let's say with virtual reality, 6 degree of freedom motion controllers, head tracking and so on, sample-based systems start becoming very, very limited. Let's skip this slide. This is basically a cue sheet. This is basically what it looks like to be a sound designer working on a game or a film or a piece of theater. You've got a bunch of, this is a lot of lights over here, but basically it's the same thing for sound. You've got lots of things that you need to fill in, and for each cue you need to make a sound effect. You've got lots of ways of processing sound in games, like for example, you can randomize samples, you can pitch shift samples, you can crossfade, or you can do something like granular techniques, where we're starting to approach something closer to the procedural method. So if we go back to games, on the graphical side, we'll see we have games like Myst, where suddenly, for that time in the early 90s, the graphics of Myst were groundbreaking, because you could see so much detail, and it was nearly photorealistic back then, people said. But of course, the problem was that you couldn't interact with it. You couldn't move, you couldn't change the perspective. There was very limited interaction. And then suddenly we started seeing more and more use of sampled graphics. So here we've got video textures, placed in 3D space, mixed with kind of more procedural 3D graphics techniques. So the point I'm getting at here is that after about 15 years, we end up over here in a territory where we're using a very careful blend of both sampled images, like textures on all the buildings and the water and so on, and procedural techniques in something that starts to create something very, very organic and beautiful. So we can look at it like this. So we came from the 90s, swung to a place in the late 90s where we were using 100% 3D graphics techniques, and now we're getting to a more stable middle ground. So we take this parallel to audio. We can see that 20 years ago or more, 30 years ago, we're using these chips, these SID MOS6581 chips on Commodores, or the ad-lib chips, frequency modulation synthesis on the Sound Blaster. So games were indeed very heavily reliant on sound synthesis. And then we've gone to a space where everything has been totally sampled based on recordings. So what we're starting to see now is more and more use of procedural audio techniques in games. We've seen it in Grand Theft Auto 5, where a third of the according to them, a third of the sounds were generated procedurally. Again, Enzian Audio was born out of this real desire and need to make procedural audio available for everyone and fairly easy to use and integrate. So I like to think that the ball is swinging back towards a more nuanced use of those techniques. So here we are, computationally generated sound, also known as procedural audio. I'm going to keep this very short. I'm not going to talk for too much longer. But basically, we've got three sort of columns of procedural audio, in my view. We've got interaction, scalability, and aesthetics. These are, in my opinion, the three things that really make procedural audio important and worthwhile. So starting with interaction, this is basically what I was saying before, that in lots of modern games, still, you press a button, press X to interact, and the according sound plays. with 6 degree of freedom control or hand trackers and so on. We need more nuanced interaction. So here's an example. Apologies for those who've seen this already, but here's an example of a lever sound system. Basically, what we have here is a lever. It's a super simple and mundane object, but it's something that's notoriously difficult to, to oralize well in games using traditional techniques. So here we've got a very simple, fairly simple procedural model. Okay, so here you can see that depending on how fast or slow you move it, and depending on where the position of the lever is, you're going to get a different sound. And this is because the model was designed like this. So basically, the way it works is you can think of a kind of gigantic cog that's plucking these individual bits of a string. As you move it, the position at which you pluck it changes, so you end up with a high pitch and a low pitch. And so basically, you can make a model based on these principles with your input parameters of just the position of the slider. We can make the model a bit more elaborate, and we can start changing the size of the lever. Sorry for the audio. So as you can see, like as it gets smaller, there are more stops as well. And as it gets bigger, you only have about 8 or so stops throughout the whole motion. Okay. So yeah, as I said, so these are the kinds of behaviors that we're thinking about when we make procedural models, and in a way, it almost doesn't matter if it really does sound like a lever or not. As long as you have this kind of mechanism in the back of your mind, you start programming this consistency inside the sound, and you can start adding your own kind of fingerprint on it, your own sound design to the way you make your model. Well, more to that later. So the next point is scalability. Titanfall is a game that was like notorious for, I think, a 30 gigabyte download or something. And the majority of that was audio files. So there's a real problem in games, in the game industry, of scalability. So like people make bigger and bigger games. That means you need more and more sounds. For every single event that happens in the game, you need a sound. And for every one of those sounds, you need another, like say 5 sounds, so that you've got enough variety. So it starts getting very, very, very difficult in terms of the amount of fixed memory you need. So here's another example where we're using the physics. Oh, sorry. We're using the physics engine of Unity to trigger a model made in Heavy, which has different parameters for material, and it reacts to force and velocity of the object on the surface. Yeah, that's very, very quiet. Yeah, sorry, it's a bit too quiet to hear. Anyway, I'll just go to the end of this video here. Anyway, never mind. So here's another way of making a mapping between the model and the game engine. The game engine provides us with this physical simulation, which isn't perfect, by the way, but there are ways of navigating it. And using, by calculating these parameters, like normal, force, perpendicular to the surface, and tangential velocity, we can control 2 models that are running in the game. An impulse model, which gets the hits and the knocks, and a scrape model. Anyway, you get the idea. The more complexity you have, the more it gets just difficult to do with traditional methods. Okay, I'll just like give a bit more background on how this model works. So here we've got a resonator bank. Are you all familiar with resonators and bandpass filters and what those things are? So resonator is basically you can think of it as there are different ways of making these things, but in this case, it's just a bank of bandpass filters with different gain, frequency, and bandwidth values. So for example, let's say this is our wooden preset, or preset for wood, or for large wooden items. We get a parameter of the size and the material from the game, and based on those parameters, it changes the fixed values of our resonator. And everything else goes into that resonator. And finally, this is my personal favorite one, is aesthetics. And I guess what I want to talk about here is quickly how can we make procedural audio more than just, more than just a basic synthesis model. How can we make it actually sound good, and approach it as a sound designer? Now this is where sound would actually be really good for this one because it's very subtle. But I'll talk you through it. So if you could hear this through normal speakers, you'd hear a kind of deep drone of like kind of these squeaky. Anyway, it's going in the background. I can't see it either, but there's a door handle here which is turning. And all the sounds in this demo are using the same model of friction. So the background is using the same friction model, the handle is using the same friction model. And eventually the door, when it opens, is also using the same friction model. So by making, basically we've got the same base model, but they all sound totally different, and they're all reacting differently to your interactions. And if we put on our sound designer hats, and we consider what would we do if we were working in a DAW or in some audio middleware or something, we'd be doing all these effects using automation curves, right? So we'd have something like 5 parameters of our friction model, like stickiness, velocity, damping, resonance, and so on. And we can sculpt all these things over time. And what we end up with is a bunch of data, basically very, very cheap, like lightweight data, and a meta parameter to drive this data. So the idea is that we're using principles from graphics again, principles of animation to drive our sound models. And this is something that we've used quite a lot in Indian, and I use myself in my own work when you need to give continuous sound a very special identity or character. Is there a switch for the lights? Right, okay. Just the front ones here. Okay, cool. Let's try that again. It's a very dark video though, so. So like here, let's look at the door, for example. We've got two parameters coming in again, our angle and our speed of the door. Here we've got what I call a behavioral layer. Think of it as like our animation controller. And this is controlling our input to the model. So the point with a handle is that like as you turn it, the pitch goes down and down, you know, because we're scaling something that's linked to the perception of pitch. So it gives you like this feedback that like, oh, it's going to open soon, it's going to open soon. It does open, you know. Okay. I studied squeaky doors for like 5 years in my life, so. Okay. Here's one more interesting thing that I haven't talked about, which is the fact that you can use your audio synthesis program to drive things inside the game as well as the other way around. So in this case, after we finally open this door and get in the room, there's a switch. And look at the fluorescent lights and the way they go on and off in random order. So every single bing that you hear from the fluorescent lights is synchronized to the light and to the texture of each light. It's a very subtle thing, but it's something that, again, be quite difficult to do otherwise.
Sorry, could you repeat that?
Oh, so in here, the fluorescent lights that you see, they're kind of binging on and off. And bing, bing. And all those bings are generated by the audio synthesis. So inside the audio model, well, inside our converted PD patch, we've got basically a number that's saying I'm on, I'm not on, or I'm on at this strength, and now I'm finally completely on. So I'm sending out numbers for the left side and the right side of the tube. With those values, I'm modulating the light and the texture, so you get the audio-visual synchronicity, which is all generated inside the patch rather than the other way around, which would be the conventional approach. Okay. So to summarize, and there's obviously very game audio focused, but I think it applies to more general applications as well. Got emergent gameplay, or think of it as emergent interactions. Multiplayer interactions. This means if you're, say, playing a game like Counter-Strike, you could use the interactive audio to give each other signals, or things like this. Music from the environment. You can blend the audio into the music and into the environment. And again, I wouldn't worry too much about the user-generated content. Doesn't really apply over here. Okay, so I'm going to do a last few slides on Heavy, introducing Heavy, and then we'll start using some Unity. Has the USB key been going around, by the way? Yeah, cool. All right. So Heavy, or Heavy CC, stands for the Heavy Compiler Collection. So Heavy basically arose from the need to embed synthesis, a PD-like synthesis, into runtime environments for multiple platforms. So before there was Enzian Audio, there was a company called RJDJ, and they made a lot of applications using all the sensors possible on the first generations of the iPhone. And that was using libpd. I don't know if you've heard of libpd, but libpd is basically PD running, like the whole of PD running in the back without the front end. So you're just like giving it a patch to open and sending messages. Now libpd is good for that. However, the problem is that running all of PD in the background is a big performance issue. And for any kind of real work, it's very difficult to navigate and work with libpd for a project. And it's definitely not optimized for performance. So what Heavy does is it takes pure data patches, which are made of text code. If you look at the PD patch and the text value, you'll see that's all text, numbers, lines, and so on. These patches are parsed by the compiler, and it's turned into something called Heavy, which is basically an intermediate representation. Think of it like JSON files, which are describing the PD graph. From this layer, we generate the C and C++ source. So basically, think of all our objects like our oscillators and our filters, our plus, multiply. All those operations are rewritten specifically for platforms and specific hardware. And finally, from there, Heavy also includes wrappers, generators, which turn the C code into Unity plugins, VST plugins, web audio JS plugins, Wise audio middleware. There's a bunch of different targets, basically. So Heavy used to work like this up until the end of August, before we open sourced it. You'd send your PD file to the website. The website gave you a nice interface. You had a username, a profile. Put it through Heavy CC, put it through our enormous build farm, and then, it's a joke, and then that gives you back a plugin. Yeah. Now Heavy looks like this. The whole tool is downloadable. You just use it from the command line. It's a simple Python script, and from there you get your plugin back. So I'm going to go through Heavy CC at the very end, as I said, because I know that it was potentially a bit problematic to install all the tools that were required. And I think also, in hindsight, it's maybe a better way to learn Heavy by using it first and the products of it, rather than getting into the nuts and bolts of compiling patches. Oh yeah, there's a Bela target as well, I want to say. Yeah, okay. So how is the USB key? Where is it at the moment? Okay, so in this folder, you're going to have 4 things. There's Heavy CC, which is basically exactly what you'll get if you clone the repo right now. You've got some PD patches over here. I've got a bunch of interesting patches, which we'll go through soon. And this is the file that we want. So if you double-click this file, or actually, let's do this. If you open Unity, let's all open Unity. And let's create a new project in Unity. By the way, if anybody gets stuck, just let me know so that everybody can catch up. Just put it wherever you want and call it anything you want as well. I'm just going to call this Soundstack2018. And create the project. Okay, and eventually you should end up with a scene kind of like this. Okay, is everybody there? Okay, so once you've got that open, just double-click on this this Unity package here, CGA Workshop Soundstack2018. And you should end up with a window like this over here. That could be that you had already imported them into Unity, so that's fine. Let's see. Show me your Unity project. Oh yeah, you need to download a new version of Unity. So you want to have, yeah, if you're using Unity 5 point something, you probably want to, you might run into some trouble. It should still work, but you might run into some trouble. Like here, there's a kind of error.
It's kind of just updated.
Yeah, if you update to, like 2018 is the latest one, if you can do that. I'll go through the rest of this. You can follow along. You have the slides there as well, and yeah, cool. All right, so once you've got that, just press import with everything selected. Oh, the screen is so big you can't even see him.
Do I just import this?
Yeah, import everything. Yeah. That working? Cool. All right. So over here, inside this heavy folder, you'll see we've got a bunch of plugins. Ducky, Fireball, Nypd, Whoosh, Wind. We're going to work with this Meep plugin for the time being. So I'm just going to walk you through getting a very, very basic plugin set up in Unity. So how many of you have used Unity before? OK. And how many have never used Unity before? OK, cool. Let me give you a quick crash course in Unity, like overview of how it works. So basically, Unity consists of, by default, these four windows here. This is our scene. It's our 3D scene where we can place our objects. We can move them. For every object in the scene, we've got a description here in our hierarchy, as you call it. And when we select an object, we've got information on that object on the right-hand side. So common to all objects in Unity are transforms. Okay, so every single object in the game has to have a transform. And the transform defines its position in space, its orientation, and its scale, okay, relative to world space. And the way Unity works, there's quite a common approach for game engines, is that it's called an event component system. So every object has components. So this object becomes a camera as soon as it has a camera component, okay? And this is important because the way we're going to add our audio plugins is as components on the objects, okay? So the camera, for example, has already, by default, an audio listener object. And it is this audio listener which is going to basically compile all our audio sources from the environment and attenuate them and pan them according to where our audio listener is. OK. So what we're going to do now is we're going to add a very basic object. So we can click on Game Object up here, 3D Object, and let's select Sphere or Cube, anything you want, really. You can even make an empty object if you want. Okay. If you want, you can rename the object. I'm going to call it the Meep Sphere. So now, inside our project viewer over here, we've got a folder called Heavy. If we go inside Heavy and inside this Meep folder, you'll see this this file called Heavy Meep AudioLib. Okay. So all the plugins that we have in Unity are going to look like this. There's a Mac OS folder and a Windows folder. These contain the compiled libraries, all the audio code basically, which is platform specific. This over here is our C# script basically. Just think of it as our central interface to the sound model. Okay. And all we need to do is click and drag the script and move it onto our sphere. You can either do it like this, or you can also do it like this onto the sphere, straight into the 3D space. Okay. Now, if that's worked for you, if everybody's done that, you should be able. Okay, so you should see an audio source over here and our script over here, heavy meep audio lib. And this has two sliders, frequency and gain. Okay. So all we need to do now is literally press play. And we've got our sound coming out already. So over here, we can in real time interface with the model. Okay. Is that working for everyone? Yeah, exactly. Oh, and then if you select the inspector over here, yeah, then you can scroll down and you'll see the interface for the, go down a bit further. Yeah, our frequency and gain parameters, so that's our sound model. Okay. So, how is everybody with writing a little tiny bit of code? Well, let's try it. Unity can seem a bit scary sometimes, especially when you dig into the code, but actually it's a very, very friendly environment, and it's very fun for prototyping stuff. So if you're familiar with Arduino and processing and so on, it's a little bit more demanding than that, but it's quite easy to get a hang of. So I'm going to walk us through making a basic script to control the movement of the sphere. Sorry, to map the movement of the sphere to the sound, this beeping sound, okay? So we're going to click on Add Component over here. And let's call it, Meep Audio Controller or something. And then you want to press New Script. Okay. So you'll end up with a new component over here in your inspector on the right. And if you double click that, it should open up an editor. Except, and you can change your default editor. I'm just doing this here because it should default to something for you already, but for me I've changed it. So I'm gonna.
So it's asking me like in Visual Studio, actually it's downloaded all the packages.
Does it say you need Visual Studio? Okay, yeah, you may need to download that to get the autocomplete. You can also use a standard text editor, but it won't give you the autocomplete solution. Okay, so if you're having problems with Visual Studio or like it wanting to launch some kind of complicated big editor, you can go on Unity Preferences or Command comma, and then External Tools. What's happened here? Missions. just I'm going to use Sublime Text. Okay. All right, so to open the script will have been created over here. You can double click on this field over here, or you can double click down here. Okay. Okay. So what we're basically going to do is what we need to do is we need to get a reference to this component inside this component so that we can talk to this component from this component. Okay. Now that object, if you don't want to write the script, don't worry. We'll go in the next project. It already has the completed thing, so don't be pressured to follow all the typing. You know, I know how it is. So basically, what we need to do is need to create a local variable of the type heavy meep audio lib, and we'll call this our meep audio. Actually, like, really don't worry about typing this along because it's quite a lot, actually. But basically, meep audio equals get component. So what get component does is it looks through this specific object. So whatever the script is attached to, it will look through the entire component hierarchy over here on the right. And it will try to get the component that you specify. So in this case, I'm specifying heavy meep audio lib. Okay. So now inside update, we can start sending parameters into the patch. So let's say I've not done this for like 5 months and I forgot how to do it. There's some great documentation on the GitHub page. Sorry, I'm just going to leave this open on the side over here. So we go into GitHub. Ah, I've got no internet. Shit. Well, if you were to go onto the GitHub, I have no internet, sorry, so I can't show this. But there's some documentation if you scroll down and select the Unity link, and it explains all the functions that are in there. So I'm going to copy this from here. So every one of these libraries, these audio libraries for Unity, has a function called setFloatParameter. Okay? And this is how we send values into the patch to control the patch. And this parameter is a variable inside the patch as well. So you'll have to say heavy meep audiolib dot parameter dot frequency, and that is our frequency parameter. And here we can provide any value we want. So I'm going to tell it I want 333 hertz. And it's C#, so we have to add an F at the end of the floats. Again, don't worry if you're not following this. We're going to go to less scripty stuff. I also wanted to show you how to do it. Okay. So we save this and we go in Unity. Sorry. Check our console to make sure there are no errors. And then we press play. And as you can see, it switched it back to 333. Okay. So now let's say we want to control the frequency of this sound with the Y position of the sphere. Okay. That is very easily done in the script as well. So to do that, we can say, what we have to do is we have to get our component, our transform component, get the value, read that value, map it to something that makes sense for our frequency range, and then set the frequency value, okay? So the way we get our position is we don't need to get the component. We don't need to use this function because every component has a transform. So all you need to do is say transform dot position, okay? This is our position. And we're going to say float, actually, float frequency equals transform position. And let's say we want to map the range of 0 to 10 to a range of 0 to 1,000. So let's just multiply our position by 100 for now. Save that. Oh, there's a problem here. We need to say dot y. Sorry. Okay. Does that make sense to everybody? What's happening here? Despite the new language and new environment and so on, all we're saying is there's our frequency value. Take the y component of our position, multiply it by 100, set that to our frequency, and finally here, we replace our number here with frequency. Okay, save it. And if we run it and select our sphere, up here we can change the y value. Yeah, it is cool. It's mega cool. Like as soon as you can control sound, it's awesome, you know. And that's really the most basic thing we can do. While we're here, sorry.
For someone that's completely like ignorant to all the coding thing, is there like some patterns that you can type copy and paste?
Patterns? How do you mean for?
Can I copy some already written?
Yeah. So we're going to go through some projects soon, which have like a bunch of scripts and helper tools I've pre-written. And you can mix and match stuff from there. I'll show you. Like we won't have to dive too deep in the code. In fact, we don't have to really touch more of the code from now on. There's a lot you can do outside of the scripting environment as well. Okay. While we're here in our text editor, I just want to go over one thing, which comes up all the time in these mapping situations, which is this is all well and good, but it feels a bit like a slider, you know? We can get some more interesting interaction out of the sphere than just like moving it up and down with the frequency. What if we were to take the velocity of the sphere and use that to control the frequency? You know, kind of like a lightsaber. This is fairly easily done, but we need to do some calculations. So I'll just show you very quickly how we do this. In order to calculate the velocity of an object, we have to take the current position, and we need to take the previous position. And then we need to subtract the current from the previous position and divide that over time. And this is easily done. So all we need to do for that is, let me move this over here. We create a vector 3. Vector 3 is an internal unity type. It's just a value that contains, it's a class that contains, a type that contains 3 values. And we'll call it pos underscore prev, previous position. And at our start, we're going to say pos prev equals transform dot position. So this initializes our previous position. And now we can calculate our velocity. So we can say float velocity equals our current position, which is transform.position, minus pos brief. Okay. Now the thing with doing this is that when you're using a you call it a clock-based system, something where you're rendering frames every time, you're not guaranteed that the frame rate is stable, the rate is stable. So if you just do this, then your calculation of velocity is going to be completely dependent on how fast your computer is able to generate the frames. So you need to make sure that you make it independent from that. And the way to do that is to take this calculation, we put this in brackets, we can divide by the time interval. And there's something that Unity gives you straight out of the box. So if you say time.delta time, this is our interval here. And then finally, there's one last thing we have to do. Anybody know what we have to do?
Remove frequency in the Nypd thing and put velocity in there.
Oh yeah, there is that. But before we even consider sending the value in, there's something we need to do. Let's ignore this for now.
The velocity is vector 3 and not float.
Yeah, that's something I hadn't actually noticed. Yeah, okay. Vector 3. Well, actually, it is a float. We're going to turn it into a float soon. But yeah, you're right. At the moment, it's a vector 3. Well, the thing I was trying to point out is that posprev is not updating. So if we were to do this, we wouldn't be actually calculating the velocity. So what we need to do is say posprev equals transform.position. And obviously, it's important to do this at the end of this loop so that we still have our previous value. Okay, so now we want to take our velocity and want to map it to frequency. But the problem is we don't know what the range of velocity is, right? Like we don't know if it's like 0 to 1 or if it's in the range of 1,000. So we need to figure out what our range is before we can map it. Otherwise we're just shooting in the dark. So to do this, we can print the value to the console. And in Unity, you do it like this. You say debug.log. And then you put whatever you want in there. So if anybody's familiar with Java, by the way, C# is pretty much more or less, for all it matters to us, the same thing as Java. It's very, very, very similar. OK, so I'm going to log our velocity. Okay. So now if I go back into Unity, and we start playing with this y value up here. Again, sorry, I didn't make this clear, but you can either type the value, or if you go over here so the cursor turns into 2 arrows, you can do that. OK, in case it wasn't clear. OK, so now over here we've got our velocity. And we notice 2 things. First of all, as you mentioned, it's a vector, and we need to get the magnitude of this vector in order to get an interesting velocity. But we also start seeing the scale. And since we're only moving it on the y-axis, this is pretty close to what our magnitude of the vector is going to be. And we see that the values are changing between, I don't know, maybe 0 and 400. So let's calculate our frequency again. Float frequency equals our velocity now magnitude. This is going to be the last bit of scripting for today, by the way. So like, I just wanted to show you this. Magnitude automatically calculates the magnitude of the vector. So if it's basically the distance to the origin of the vector, and that is basically our overall velocity in all directions of space. Okay. And then we want to scale this magnitude to a meaningful frequency range of values. So we had values between 0 and 400. So that means let's divide by 400 for now. Again, you need to add the f at the end to specify it's a float. And then we can say frequency. So this maps it. Okay. So now we've mapped our velocity range of 0 to 400 to a frequency range of 0 to 1000. Okay. And now if we play this, oh, sorry, we also actually need to send the value into the patch. Okay, so now we've got to a stage where we've got a meaningful interaction. And now comes the next, now is when it starts getting more fun. We can say, okay, it works, but I want to scale it differently, you know? So let's say this number over here, why don't we make that a parameter so that we can set it in Unity, okay? Let's say we set it to a parameter called scale factor. Okay. Public is saying that it's that this is a parameter of the class that can be accessed from the outside. You don't have to be this class in order to see it. And if you do that, you'll see that you end up with a field over here. You see? Scale factor over here, and you can set it from outside the script. Okay, I'm going to change this with scale factor over here. Now, we can run the game. Let's make it higher. Let's set it to, say, 8,000. Okay, and this is 80 or 90% of the work I find myself doing when I'm doing this stuff, procedural audio development. You've got your basic system set up, but all you're doing is setting these magic numbers, so to speak, until it feels right, you know. And this is where all the sound design happens, interaction design, you know. So you can go ahead and save that scene if you want, or you can just, you know, if you don't want it, you can get rid of it. In Unity, it's good to stick to a meaningful folder hierarchy. So I tend to keep the scenes in a folder called scenes, scripts in a folder called scripts. I'll just call this my test scene or something. And what time is it? Now we're at a point where, I don't know, does it make sense to have a break at this point? Or?
Sure.
Yeah? Should we have a 10-minute break? But let's have questions first, yeah?
Oh, just a really quick, I think I'm doing something really stupid. How do I everything's working, but I can't actually touch the ball and find it in the scene. Is there something I should press to be able to interact with that when I play it?
Yeah, yeah, because when you're in play mode, you're in the game window, right? So you can't select it. Yeah, yeah.
Navigate the game window.
Well, the thing is you can't navigate. You can go into the scene window, back to the scene window while it's playing. So let's say I'm playing here.
Oh, right.
You can go back to the scene video window. Or you can select it on the hierarchy here, you know? So every one of these objects is selected here, even when the game is running. You see? It's a bit of a weird interface, but you get used to it.
Is it a problem for sound?
All right, is everybody ready to continue? All right, cool. Let's go on. In our scenes over here, we've got a bunch of example scenes that I've added. And we're going to open whoosh motion over here. All right. So this whoosh plugin is basically what it says on the tin. It goes whoosh based on a velocity parameter. So just to show you, I'm going to disable these two scripts over here just to show you how it works. Okay. There are a few parameters we can set, like the mix. Okay. So you might have noticed that just like with our sine tone, like using the delta, the velocity, we need to activate this with movement, with a value that's moving and not with the absolute position value in order for the sound to make sense. Okay. So I'm going to stop this and re-enable these two scripts. So we can look at, actually we don't need to look at it. Basically, I'll just tell you what these scripts do. This one is basically a script which makes the object move in 3 dimensions with sinusoids. So it's just going to keep swinging like a pendulum back and forth. And we can set the frequencies of motion and the gains of motion over here. And over here, we've got our object audio whoosh controller. We can open this. And this should look fairly familiar to you. We're taking our audio lib, our whoosh audio lib, instantiating it, getting the component. We're also getting this component called our object transform controller. And from this component, we're getting this function, which is get velocity. Okay. So everything inside the script, it's already calculating the velocity. We're just grabbing it, and we're sending it to our audio lib based on a scale factor. Okay. Just like in our previous example, we're using a scale factor to change how the movement affects the whooshing sound. Okay. So we press play with all the scripts enabled. You should see the ball moving. Okay. And we can change some parameters here. Okay. So as you might notice, is there sound coming out of here? Yeah. The sound isn't really spatialized very well. Like you might hear, there might not even be any panning or anything. Okay. So what I'll show you now is how we can use something called the Resonance Audio SDK to binaurally spatialize these sound sources. There's two reasons I wanted to show you this today. One is obviously because there's been a workshop on spatial audio, and it's a very relevant topic. But the other point, which is quite an important one, is that when you're working with procedural audio and audio models, you're often considering the sound before it actually is spatialized or diffused through a room. It's kind of like you're modeling a point source, you see? So if I flick the scan, you're just going to hear it as if you were to attach a contact microphone like that. It's a very dry and aggressive sound. So as soon as you put it through some good spatialization, it adds an element of realism to it that is very important to carry the sound, and give it a kind of weight of realism. So I've already included resonance audio in here. If you're doing this for the first time in your own project, you can download the Resonance SDK from the Google website, the relevant one, and you can just import the Unity package like that, just like we did with our package. I've already imported all the relevant ones, so we don't need to worry about it. And you'll notice that it's imported by seeing Resonance Audio up here. Yeah. OK. So the first thing we need to do is we need to go on Edit and Project Settings and Audio over here. OK. Everybody got that? Yeah. OK. This will give you this menu over here on the right. So what we need to do is change these fields over here, Spatializer plugin and Ambisonic Decoder plugin. Now, all you need to do is set this to Resonance Audio, and this also to Resonance Audio. OK. Sorry. Let me just get that back up there so people can see. Yeah, like this. Now this makes, I've done ambisonics and binaural spatialization like for a while. I did it like 8 years ago or 5 years ago with game engines, and it used to be extremely difficult, very complex setup. Nearly impossible to do. The integration with game engines was non-existent. So the fact that this exists and it works so well is like quite incredible. It's very, very an easy setup considering all the stuff that needs to be set up. What Resonance Audio does basically is it takes any of our sound sources, whether it's a normal, regular audio file sound source or one of our plugins, and it tells Unity, OK, don't send this to Unity's basic output bus. Send it to the special Resonance Audio output bus, which takes the source. It encodes it into, I think, potentially 5th order ambisonics, a very high order of ambisonics. And then it decodes it back. Usually that happens through like an array of virtual speakers, which is following your head. And as you turn it, calculates the corresponding impulse responses for your ears. I think that's how it works. Probably it might be a different technique. But basically it means that when you put on your headphones, you'll hear binaurally 3D spatialized sound. Okay. There's one more thing we need to do. We need to select Spatialize over here inside the audio source field. And we also need to select Spatialize Post Effects over here. Okay. Up here in Spatial Blend, we need to move it to 3D from 2D. This basically adds distance attenuation and panning. And finally, the last thing we need to do is select this circle over here. And we choose this master output bus, which is something that Resonance Audio automatically adds to the project. on the circle here. Yeah. Okay. So now if everything is set up properly, you should hear everything spatialized through headphones. It won't sound the same through the speakers, but so it might be very quiet. And that is because it is quite far away. And you can change the attenuation curve over here. But what we can do is we can take the camera, and if we use the Z coordinate here, we can move the camera forward into the trajectory of the sphere. Okay. We can also change our velocity scale factor over here. Let's go back a bit. Okay. So that should be rendering binaurally, yeah? Okay. So fun thing you can do now is if you go on the hierarchy window over here, and you just copy and paste this model a few times, it's going to instantiate the same model with all the same settings. So I can do that. Okay. I mean, you can add loads of these. At some point, you know, you might reach a limit, but yeah. And then we can move our camera again into the middle. Okay. So obviously, if this was, if you're using a head-mounted display with head tracking, this would, you know, and the corresponding Unity setup, it would, you know, change everything depending on whether you're looking at them or not, whether you're inside them, you know. And that's a very powerful thing. Cool. Next, we can have a little bit of fun with this. Let's do like a little 10, 20 minutes of like just exploring Unity and a new scene. If we go on Scenes and select Windscape over here. Sorry. Windscape. Okay, again, we've got a sphere on a black background. However, we'll see that we have a different audio source, and it's called wind. Okay. What this does is it just generates random filtered noise that corresponds to the sound of wind. So if I press play, let's move the camera forward a bit. We can play with these parameters a bit. Change the size. Okay. So if you read Andy's book or check out his talks online, you know, there's a very good explanation of how this is set up. And we can look at the PD patch soon, so we can dive into the PD patches and look at how these models work. But wind is basically a very, very simple thing to simulate it. You just take pink noise, or white noise potentially if you want. You put it through a filter, like a bandpass filter. The movement corresponds to gusts of wind, movement of the filter. The resonance of the filter corresponds to the symmetry of the object. So if you've got a stick moving in the wind, you're going to get sound that sounds more like this. If you've got like a more kind of diffuse, kind of complex object, you're going to get a sound that's more like this. Okay. If you've got a big object, it'll sound like this. If you have a small object, it'll sound more like that. Okay. So what I thought we could do, like as a fun exercise, just to get familiar with this, is we could make a little windscape. So if we go in our scene over here, instead of our game view, select scene. Make sure 3D is selected. Over here, we've got our transform tools. You can select them with WERT. Well, WER are the main ones you want. And you can move them around. You'll see there's a sphere over here, this blue one. This sets the attenuation of the source. So the bigger it is, the longer the attenuation curve. Okay. So what we could do, I thought might be quite fun, is if we take a few of these and we just move them around, and we just make a windscape basically. So just to demonstrate, we play our game here. We've got two sources. Notice we can move them around, and it's best to do this with headphones as well. And for each source, we can select different sizes. So we can make this one like a really big size. We can add another one here. And then once you've got your different wind sources set up, you can take your camera and you can, for example, just move it through the sources. Now, apologies, I didn't really add any first-person motion controller or any interesting way of controlling the camera, but I thought this is enough to demonstrate the principles. But yeah, if you want, feel free to let's make a little windscape for a few minutes. Try and copy and paste these things. One thing to keep in mind when you're doing this is that you're probably gonna want to do this while you're in play mode. Okay, so you can select this and you can do Command C, Command V, copy and paste, or you can just do Command D or Control D to duplicate. Duplicate your spheres. Now the important thing is, if you press play, and I've duplicated a bunch of objects here, you're going to lose all your objects. Okay? They're going to go away. And that's because the play mode is done for prototyping, for very quickly setting parameters. If you've made your scene, let's say we've got our 8 objects over here, then what you want to do is you want to select them all, and you want to copy them. Okay? And when we stop playing, we can paste them back in, and they'll be there again with their settings. Okay, so that's the best way to keep them.
And if you had them beforehand, they would stay automatically.
Yeah, yeah, exactly.
Only when you're playing.
Exactly, yeah, yeah. All right, how's everybody getting on with that? Cool. Yeah, if there is no audio, it's probably a resonance bug, and I'm not really sure at the moment what's causing it. But things to try are to make sure that your project settings have the right spatializer and decoder plugin selected. If that still doesn't work, then you might want to try and download the latest Resonance SDK, but I'm not really sure why that would solve it, because it's the same file I gave you. But you may want to re-import. That would be one thing you can do. If you go on Unity Resonance SDK and import this package. Yeah. OK. Well, let's save this for now. I'll show you some other stuff we can do. I'm going to go to Resonance Basic. Okay. So if you open Resonance Basic, you should see a cube with some kind of pinkish red light. And if you scroll down on the inspector, you'll see three buttons: Piercer, Whale, and Yelp. And these are basically 3 modes of the Nypd Siren, police siren. So if you press play, You should hear it coming spatialized. Hours of fun. Yeah. But yeah, that's just an example of a different sound source that's not noise-based. If you open Fireball over here, this is basically, remember with the whoosh spheres, we were kind of copying and pasting them and having lots of them. This is kind of a nicer version of that with a little interface. I included this just as a nice thing to have, but also you can see, you can dive into this project, look at the scripts. The scripts are slightly more, well, they're more advanced than what we've been looking at, but I'll walk you through how it works. We've got a Fireball manager here. So what this is, I'd call this a particle system, an audio particle system, because we've got one entity here, this manager script, which is instantiating, so it's creating lots of these scripts, the Fireball sound model scripts. And it's setting some global parameters. So if I press, and we've got this UI over here, which is a Unity thing, this canvas, and these things are mapped to sliders inside the script. But I'll leave that for you to explore. But if we press play, actually we can full screen this one. We can spawn fireballs, make them go fast or slow. And we can set the size as well. And you can see that it's actually quite powerful, you can have loads and loads of these kinds of objects, and they're all dynamic and moving and changing in response to their movement. So there's, I guess, just a very quick and simple example to show you the capabilities. So I think I'll leave it there with Unity for now, because this is basically, I'm kind of doing this workshop backwards. So we're starting with why do we use it? How do we use it? What's the point of it in the first place? So I think that kind of shows you that. Next, I want to dive into the PD patches a bit. So it's a bit of a change of topic, because now we're looking not at the game, but at what happens before we put the thing in the game. Again, feel free to patch along, but don't worry if you don't. It's more about showing you the basic concepts over here. So inside our folder, we've got a folder called PD. And we've got lots of, all the models that we're using, plus a few more. There's also a zip model and a rubber ducky model. So let's start by looking at the meep model, okay? The one that was just making a beeping sound.